Assalamu alaikum everyone. We are going to study today about the voltage and current waves. Just a brief overview of what we have done in the last lecture. So we started from the long transmission line and we considered a small segment of that particular long transmission line in which we have impedance for that segment delta x, and then we have the admittance in the shunt branch delta x, and we have voltages before and after that segment. So what we have done, we have started from the voltage and current equations for that particular segment. So we have applied the KVL and KCL at this node, and for example that was node A, and we found the voltage and current equations in terms of constant A1 and A2, and also the exponential terms e raised to gamma x, where gamma was the propagation constant, and we then termed the value under root y by z equal to characteristic impedance. After that we applied the end condition, and at the load end is equal to 0, because at the start of the transmission line x was equal to L, and at the load end it was equal to 0. The current value was IR, the current through the load, and the voltage was VR. And after solving these two equations Vx and Ix, these two equations V and Ix, we found the constant values A1 and A2. So we then calculated the generalized equations for voltage and current in terms of hyperbolic functions of cosine and sine, and Zc was the characteristic impedance. Later, to find the voltage and current values at the start of the line, we found that x is equal to L, and the voltage was equal to Vs, the current was equal to Is. So the final equations were Vs is equal to Vr cos hyperbolic gamma L. Gamma was the propagation constant, L was the length of the line, and IR was the load current, Zc was the characteristic impedance. So these two equations we found at the end of the last lecture. So today's topic is voltage and current waves. A very basic overview of what will be the effect of inductance and capacitance of the transmission line. Whenever we apply the voltage in the start of the transmission line, for example if we have a switch and we close it at the sending end, the voltage does not appear at the end of the line instantaneously. So there is some time, a finite amount of time that is required for the voltage to appear at the load end. So basically this is due to the effect of inductance in the transmission line. Inductance is actually physically not present in the transmission line, but there is effect of inductance, and the voltage will take some time to gradually build up over the line. Similarly, there is some time for which is required for the gradual charging of the capacitor, and the current will take some time to travel from the sending end to the receiving end. Due to these effects, the inductance and capacitance effect, we call them the voltage and current waves. So because they are taking some time to travel from the sending end to the receiving end. So now if I have to start some basic derivation for the voltage and current waves, we will start from the equation that Vx is equal to A1 e raised to gamma x plus A2 e raised to minus gamma x. So that was the voltage equation if we have to find the voltage at distance x, for example. Now we know that gamma is the propagation constant, and it is equal to alpha plus beta j. If I'll put this value of propagation constant in the equation, so Vx will be A1 e raised to alpha x e raised to beta x j. Similarly, the second term will be A2 e raised to minus alpha x e raised to minus beta x j. So there will be two terms in the voltage equation. Now this particular equation, it is in phasor form, so it is the phasor value. Now if I have to convert this into time domain, so that will be Vt for the time domain and x for a particular distance x of the transmission line, under root 2 real value of A1 e raised to alpha x e raised to j omega t plus beta x. Similarly, for the second part of the equation, that will be under root 2 real part a2 e raised to minus alpha x e raised to j omega t minus beta x. Actually, there should not be minus here. So what we have done, this was the phasor value of the voltage. Now if I have to convert this into the time domain, so it will be Vtx. T is for the time domain and x is the distance at which that we are calculating the voltage value. And this is the RMS value. To convert it into the peak voltage, we just have to multiply it by under root 2. So the first and the second part of the equation will become under root 2 real part of a1. A1 is the constant, e raised to alpha x. Alpha is the attenuation constant, and e raised to j omega t plus beta x, and beta is the phase constant. So this will be the equation of voltage in time domain at a distance x. So now if I will just say that this is A and this part of the equation is B. So now we have two parts. First one is with the positive values of alpha, e raised to alpha, and the second one is with the negative value of e raised to minus alpha. Now if I will start from the end of the line, at the end of the line x is equal to 0. If we move from the receiving end towards the sending end of the transmission line, A will become a larger value. So if at the receiving end x is equal to 0 and at the sending end x is equal to L, so what do we have? From receiving end towards the sending end, the e raised to alpha x value, it will become larger, right? So at e raised to 0 it will be a value 1, x is increasing, so e raised to alpha x value will be increasing. So I will write it down that a will become a larger value because e raised to alpha x will increase with increase in the value of x. Finally, we can say that at the sending end, the portion A of the equation will have the largest value, and at the receiving end, it will have the smallest value. So we can call this equation, this A part of the equation, as incident wave. So what do we have? At the receiving end, the A part of the equation has the smallest value. At the sending end, it has the largest value. So it is moving from sending end towards the receiving end, and that's why it is known as incident wave. For the second part of the equation, starting from x is equal to 0, B will become a smaller value as we move towards the sending end. Why? So exponent e raised to minus alpha x will decrease with increase in the value of x. So the second part of the equation has the maximum value at the receiving end. So it will decrease as we move towards the sending end. That's why it is known as reflected wave. We have a voltage equation. There is one part that has e raised to alpha x in it, and the second part has e raised to minus alpha x in it. So if we start from the receiving end, the x is equal to 0, and if we are moving towards the sending end, the x is increasing with the movement towards the sending end. So that's why the A portion of the equation will increase as we are moving towards the generation point or towards the sending end of the transmission line. So that's why it is known as incident wave. In the second portion, we have e raised to minus alpha x, and as the value of x increases, this term decreases, e raised to minus alpha x decreases, so it has the maximum value when x is equal to 0. So e raised to minus alpha x will become 1, and as we move towards the ascending end, this value will become smaller and smaller, and the b part will be the smallest value at the sending end. So that's why it is known as reflected wave, because the maximum value is at the receiving end and the smallest value is at the sending end. So this is the concept of incident wave and reflected wave. So I can write the equation Vtx is equal to V1 Tx plus V2 Tx. So I have divided it into two parts. The first one is the incident wave of the voltage and the second one is the reflected wave of the voltage. And if I have to further explain it, so V1 Tx is equal to under root 2 A1 e raised to alpha x cos omega t plus beta x. Similarly, V2 Tx is equal to under root 2 A2 e raised to alpha x cos omega t minus beta x. So these are the voltage equations. The first one is the incident wave, this is the incident wave, this is the reflected wave. Similar equations can be derived or can be assumed for the current wave. So we have current waves as well, and these are incident and reflected. So the current waves also have two parts, incident wave and the reflected wave. Now for example, if I have to find the maximum value of the equation, I will start from the first part. I will write it down again. V1 Tx is equal to under root 2 A1 e raised to alpha x cos omega t plus beta x. Now what I want is to find the maximum of this equation. So if I have to find the peak of this voltage, so this value should be equal to the maximum value, right? So this whole term cos omega t plus beta x should have the maximum value, and it will be maximum when omega t plus beta x is equal to 2k pi, and where k is equal to 0, 1, 2, so on, right? So if k is equal to 0, so this will be 0, and the cos 0 is equal to 1. Similarly, cos 2 pi is equal to 1, cos 4 pi is equal to 1. So this will be the maximum value, and from here if I have to calculate the value of x, that will be x is equal to omega t over beta minus 2k pi over beta. So this x is actually the distance from the sending end at which we are calculating the voltage. So if I have to find, if this is the distance and if I have to find the velocity, for example, and velocity is actually change in distance over time. So if I have to find the velocity, I will take the derivative of this equation. So taking derivative of the equation A, that will become dx over dt is equal to V is equal to d over dt omega t over beta minus 2 pi k over beta. Now this value, it's a constant, and if I have to write the velocity equation, that will be omega over beta. So I am taking only the derivative of the first part, omega t over beta. Dt over dt will be 1, so omega over beta. That is your velocity equation, and that is actually known as velocity of propagation. So this is the velocity of propagation of waves. So it can be a current wave or a voltage wave. So if you have to find with which velocity actually voltage is traveling from the sending end to the receiving end, you have to divide omega by beta, and beta is the phase constant, omega is 2 pi r. Now if you have to find the wavelength, for which the phase shift is 2 pi. As we know that voltage is actually a cosine or sine function, right? Cosine or sine function. So what is wavelength? It is actually distance, right? Distance that will be covered by the voltage wave for the whole cycle, right? So the distance that after which the angle shift is 2 pi, if I have to find that, that will be beta lambda is equal to 2 pi. Now what we want the wavelength, right? So wavelength unit is meter, and for the phase shift the unit is radian. So now if I have to make meters or wavelength equal to 2 pi, we have to multiply it with some value that will make this whole term equal to radian. So this beta is the phase constant, and from the last lecture we know that the unit of the phase constant is radian per unit length, right? And this lambda is actually also the length. So if it is radian per meter, for example, multiply by meter is equal to radian. So meter will cancel out, so it is radian is equal to radian. So to find the wavelength of the waves, we have to use a formula 2 pi by beta, where beta is the phase constant. Now we have two equations. This is the second equation. The first one was for the velocity. Velocity is equal to omega by beta, and the second one was lambda is equal to 2 pi by beta. So in both equations we don't know the value of beta. We don't know that, right? So now to find the value of beta, let's consider a lossless line. So what is a lossless line? In which there is no attenuation, right? So this is your attenuation constant. So if attenuation constant is equal to 0, there are no losses in the transmission line. So propagation constant, that will become gamma is equal to beta j. So in the lossless line, gamma is equal to beta j, and also in the lossless line conductance is equal to 0 and resistance is equal to 0. So if I have to define the values or the parameters of the transmission line, that will become 0 for the lossless line are attenuation constant 1, conductance 2, and the resistance of the line. So these are the three parameters that will become 0 for the lossless line. Now if I have to find gamma, that will be alpha plus beta j. This is equal to 0, and it's also equal to under root zy. And if conductance is equal to 0, z is equal to r plus j omega l. So if this is equal to 0, z is equal to j omega l. And for the admittance, it will be g plus j omega c. G is equal to 0, so y is equal to j omega c. From here we can write beta j is equal to under root j omega l into j omega c, and taking square on both sides, that will be beta square j square is equal to j square omega square lc. This will cancel out, and beta is equal to omega under root lc. So after considering the lossless line, we have calculated the phase constant value, and in these two equations for the velocity, now we know the beta omega is equal to 2 pi f. We can calculate the velocity of propagation of the wave, and for the wavelength we again now know the value of beta. So 2 pi by beta, that will give you the wavelength of that line. So now the equations will become velocity of propagation. V is equal to omega by beta, omega by omega under root L C. So that is the value that we calculated, and V is equal to 1 over under root L C. Similarly, we can find the wavelength or distance for which the phase shift is 2 pi. It will be lambda is equal to 2 pi by beta, right? And if I'll put the value of beta, it will be 2 pi over 2 pi f under root L C. So 2 pi will cancel out and it will be 1 over f under root L C. So these are the two equations that we calculated. Now there was one more parameter that is known as characteristic impedance. And ZC is actually equal to under root Z by Y, right? So here we have calculated Z and Y. So I'll put the values of Z and Y in this equation. That will be J omega L over J omega C. So ZC is equal to L over C. So for the lossless line, the characteristic impedance will become resistive. For the lossless line, characteristic impedance will become resistive. So it does not have any frequency part in it, so it cannot be termed as the inductive reactance or inductive capacitance. So it is the inductance value, the capacitance value, so it does not have any frequency part. This is known as surge impedance. So the value of characteristic impedance for the lossless line is known as surge impedance. You just have to convert them into SI units in base quantities. So the SI unit for inductance is kilogram meter square per second square per ampere square. Similarly, for capacitance, the unit is S4 square. So if I'll divide L over C, that will give you meter square, second square, and second raised to minus 3, a raised to minus 2. So this is actually the unit of resistance. Now from the equations of inductance and capacitance that we calculated in the start of the semester, there were two equations for inductance. We have calculated that the formula was 2 into 10 raised to minus 7 ln GMD over GMRL. Similarly, we have found the formula for the capacitance value. It was 2 pi epsilon naught over ln GMD over GMRC. Inductance part, we were considering the fictitious conductor. So because of that, we were not actually using the radius of the conductor. We were considering the radius that was R dash. That is because of the internal flux linkage. So that's why I have written GMRL. So this is geometric mean radius for the inductance. This is geometric mean distance. Similarly, for the capacitance, this is geometric mean distance, but GMR will be different because in the capacitor case, we were considering the actual radius of the conductor. GMD is equal actually geometric mean distance, and GMR is actually geometric mean radius. For approximation, we are neglecting the effect of internal flux linkage. And if we are neglecting the internal flux linkage, then GMRL will be equal to GMRC, because now we are not considering the fictitious conductor radius. Now we will be taking the radius, actual radius of the conductor. So GMRL will be equal to GMRC. So now if I have to find the V is equal to the velocity of propagation, that will be 1 over under root LC. And if I'll put the values of the inductors and capacitor, that will be 1 over 2 into 10 raised to minus 7 ln GMD over GMR, right? And multiplication with the capacitance value, 2 pi epsilon naught ln GMD over GMR. So these two will cancel out each other, and it will become 1 over under root 4 pi into 10 raised to minus 7 epsilon naught, and this value is actually mu naught, right? So we can write it V is equal to 1 over under root mu naught epsilon naught. So this is actually the velocity of propagation of the voltage and current waves. Similarly, we can also find the values for the wavelength. So similarly, lambda will be equal to 1 over f under root mu naught epsilon naught. So that is your wavelength. And after calculating the values for the velocity of propagation, I am taking the values mu naught is equal to 4 pi into 10 raised to minus 7, and epsilon naught will be 8.854 into 10 raised to minus 12. So the velocity of propagation will be 3 into 10 raised to 8 meter per second. So the voltage and current waves have the velocity that is equal to the speed of light, and the value of wavelength will be 5000 kilometer if we are taking frequency 60 Hertz, and it will be 6000 kilometers if the value is taken to be 50 Hertz. Till this point, what we have covered is we started from the basic voltage equation Vx, and it was A1 e raised to gamma x plus A2 e raised to minus gamma x, and from that it was a phasor value. I have converted it into time domain, and from there I have defined two different portions of the voltage equation. The first one was the incident wave, because as we travels from the receiving end towards the sending end, the value increases, and for the second part, as we moves from the sending end towards the receiving end, the value actually increases. So the second part is the reflected wave, the first part was the incident wave. And from the equations, then we calculated the velocity of propagation of the waves, started from the distance value. So for the distance, if the voltage value has to be maximized, the cosine part of the function or of the voltage function should be maximum value. So what we have done, we have made it equal to 2 pi k, and from there we calculated the distance, and for the velocity we just have to take the derivative of this particular equation, and I found that V is equal to omega by beta, which is the velocity of propagation. For the distance for which the phase shift is 2 pi, I have used this particular relation, and from there we found that lambda is equal to 2 pi by beta. It is actually the wavelength or the distance for which the phase shift is 2 pi. Then to calculate the value of beta, we considered a lossless line, and in lossless line we have three parameters that will become 0. Alpha is the attenuation constant, so it's become 0. Conductance and resistance, they become 0, and from there the value of gamma, propagation constant, we got the value of beta, that is the phase constant, which is equal to omega under root LC. The second part was the characteristic impedance, and if the attenuation constant is 0 and the conductance and resistance value is 0, the characteristic impedance will become resistive, and this is known as surge impedance. Now for the values of velocity of propagation and wavelength, we put this particular beta value in the first formulas, and we got that the velocity of propagation is just the uh, function of inductance and capacitance. Similarly, the wavelength was the function of frequency, inductance and capacitance. We know the formulas of inductance and capacitance, and after calculating the velocity of propagation formula, we got 1 over under root mu naught epsilon naught, and similarly we found the formula for the wavelength. And the last thing that we found is that the velocity of propagation is actually the speed of light, and the wavelength is 5000 km to 6000 km.